Swayam Prabha. Digital India. Educated India.
Good morning, boys. Let's look at the equilibrium of several bodies connected together as a system, and then we would like to explore the equilibrium of that system. So, many times we may have to find out the forces at various important places, or many times we might even have to ask something is okay or not, something is not okay. So last time we have seen something regarding some tables and then some linkages and so on, or even the cutting player which prunes the roots or the branches of things. So it's very elaborate, and in that context, let's also explore one more problem here, interesting problem. And here, in this problem, what we have here is that is a container, like tennis ball container, which is open in this side, which is inverted and resting on the ground. And inside there are two balls here, 1 and 2. And then obviously when you invert it, one of the ball is resting on this one. This is bigger than d by 2, and then the one ball is resting on the ground also. So there are interesting things. So one thing is that you may be asked to find out what are the reactions here at A and B. Reactions in the sense that if you take the system out as a free body diagram, and then what are the forces at A and B, the internal forces will become the external forces. The reactions will be shown as external forces on that system. So there is also another question, is that for certain configurations, if the balls are big or small, at some situation there is a chance for the whole system, the whole container can tip over one of the supporting points A or C. Okay, so that is the final interesting part. So will there be a chance of this tipping, and then in which direction it might tip, under what conditions? So that is the thing. So I am not writing it to analyze the whole system for forces. So that's number one. Well, if you want to find out all the forces, it's fine. On the other hand, the thing is that find the possibility of tipping of the container So it may be about A or C. So this also it's interesting for you to find out which way it might tip. So that is the ultimate thing. So to come to that point, we have to analyze the forces at A and C. Okay. So can we get the forces at A and C? So let us see the various diagrams that are necessary here, various free body diagrams that are necessary here. So if you draw the free body diagram of of the whole system, of the container, of the system containing container and the two balls, cylindrical container and the so this is what we are looking at here, is that if you do that, of course the geometry is given, the diameter is d, and the container has a weight W0, and the two balls have two weights W1 and W2, and each ball is having size of d, the diameter. And so here, so if you are writing the free body diagram of this one, so at A and B and C, so free body diagram is nothing but separating that body which is of your interest, and then from its connected bodies, and then showing all the internal forces as external forces on this body. So we are separating these things from the ground, and so we have, which is touching here, FA and FC, and as well as the ball B is also touching the ground. So there are two balls here, and so either you can conclude right in the beginning, of course there are external forces here, W0 and W1 and W2. So these are the weights, so which also form the part of the free body diagram, and of course the geometry also you can put it. Okay, so now the thing is that, can we solve this? If we can solve this, so we need not go any further. We need not write any more free body diagrams. So if you look here, so either I might put the horizontal force here, I might not, but let's not put that horizontal force at this moment. Okay, in fact I may have to put the horizontal force also either at A or C, or more, maybe both at A and C. But if you look at the problem, all the forces are acting vertically, so there is no need for any horizontal force, right? Even if you put the horizontal force, you can immediately conclude that horizontal force has to go to 0. So that horizontal equilibrium of the forces is trivially satisfied here. So you need not really look into that. So, well, that simplifies our calculations, but the rest of the calculations involve FA, FB, FC, which are the unknown reactions which are coming here from the ground, and the other things W0, W1, W2 are known to us, given to us, the weights are given. Okay, so the geometry and the weights are all given to us, so please take that into thing. And can we solve this one? So the three unknowns are here. Unknowns are three. Unknowns are three, which are FA, FB, SC. So these are three forces, and what are the possible equations which we can have here? So we can have here the equations, two equations, only two. The one equation is trivially satisfied, so the vertical thing here, so that is vertical equilibrium, very simply FA plus FB. So the upward force and the downward forces are W0, W1. Okay, so this is one equation. So the other equation which we might get here is there is a vertical equilibrium. The other equation will come from the moment. There is no horizontal thing. So the moment is about any point if you want to take it. If you want, you can take it about A, moment about. This is if you set the moment about A, then you have this is D naught and this is diameters, or this is of the diameter is D by 2. So it is FB here, D by 2, right? And FC, D naught, right? And then we have, I'm sorry, this is FB, and then we also have the other things like W1, D by 2, and then this is W2, D minus D by 2, right? D naught or D naught. So this is total D, and then this distance is D by subtracting D by 2, as well as we also have W naught. Okay, so this is another equation, second equation. So we will not be able to solve this three unknowns FC from two equations. So what we do here is that we will look into breaking this system into smaller bodies in such a manner so we know some interactions at those connecting points. Okay, so one of the things here is that we can remove the balls. Okay, remove the balls and then remove the balls and draw the equations for the container. So FBD of the container this is the container, and also let us draw with further discussion. So we will also draw this ball B and second ball. This is the first ball. Okay, all of them we will see together. Okay, so what is that which we have here is that, so we will continue to have this force A and force B here. I'm showing all the free body diagrams right here, and then I'm going to put down the forces. So this is the container, this is the ball 1, and why I want to write them together is that whatever forces, internal forces, this with this one will be shown here as well as will be shown in the opposite sense. So similarly here, these two are actually in contact, but since they are being drawn as a free body diagrams, so we will show the external forces. So what is the thing? Then this ball is touching here. Let us see here, T. So the salient points are this. So D is the where the ball 1 is touching the container, and E is these two balls are touching each other, and F is where this is touching the container again. So again here we assume that there is no friction. If there is at the contacting surfaces, if there is any internal force, the internal force has to be normal to the surface. Okay, so now this ball has been removed here. So these two are contacting each other at this point D. So let's call this as D, right? And so there is a force here, FD, and so similarly there is a force here, F, at the point F. So the normal force here will be obviously it's a contacting force, so it is pressing each other, right? So if they're so we need not put it in the opposite direction, because if they are trying to separate out, so there will not be any force. So since they are touching each other and then they are pressing, so that's why the force has been given as FD here. Okay, so the force between ball 1 and ball 2 at point E will not be shown here, right? So anything else? So apart from this, so we have weight of the container, W0, and that's all. Okay, there's no other weights of the balls will not come here. Okay, so this is for the container. The same thing we can write it quickly. W1 here, and the ball 1 is in contact at point B with the ground, FB, and here this force between the container and ball 1 will be shown on this one like this. And then there is also another force here at point E. So at E they are touching each other, so that means that at point E here, and that will be a force Fe acting normally to the surface, and we can also say that it is going radially like this one at some angle, say phi. What is that phi? We will see the geometry just now. So this is for the body 1 and ball 1. So the same thing can be done here. So this is here. This is at point E. And again going through the normal and going through the radial. And then you have W2 and this is W1. And okay, so there are so many free body diagrams we have drawn. So this is for the whole system. This is for the container. This is the ball 1 and ball 2. Okay. So in fact, we have made use of something already, some knowledge that there are 3 forces here which are acting on this body. There's a W here, there's a F here. So all of them will have to, these two you can say concurrently, and you can make them into one force. So essentially this is one force and the 3 forces. So they have to, all of them should pass through the center. Okay, that's number 1. So similarly here, there are 3 forces here which have to pass through the center. Okay, so while doing that, that means that what is that which we have already taken into account? Can we put down all the 3 equations? So the 3 equations are force in x direction is 0, force, sum of the forces in y direction is 0, and the moment is 0 here. So the moment is 0 here is already satisfied by making the 3 forces passing through the center. Okay, so moment is satisfied. Only the forces here, horizontal forces, for example, horizontal. So this I'll put as FB, horizontal equilibrium, forces equilibrium, FB minus FP cos phi. This is horizontal thing, right? And the vertical thing is that, sorry, this is FD. And the vertical components are FB minus W1 minus Fe sine. What is phi? Comes from the geometry. We can find out just now. So I'm writing down simpler things. So this is for the ball 1, and for ball 2 also we can write exactly the same, similar one. So horizontal one, Fe cos, same angle here, cos phi, right, minus ff is 0 and fe sine phi minus W2 is. Okay, so I'm just coming back to this one. Okay, so where we only talk about the container, only the container. So interesting thing is that there are only two forces here, horizontal forces, very easy to find out. Horizontal equation minus fd plus ff is 0, right? And the vertically there is a fa plus fc, I'm sorry, this is c, I'm sorry, this is c, fc minus w naught is 0. Okay, and then this is the horizontal equilibrium, this is vertical equilibrium of the forces, and the moment, so the moment is, what is that? So essentially it is a couple here, fd and fp, these are giving a couple here. Okay, so these two are equal, so that means that they form a couple. You can use fd is equal to ff or even otherwise, okay, or leave it as it is. So this distance, let us say this distance is some h. Okay, so it is ff into h, so it is like this. Okay, we will take it about this point, so we can even write fa into this distance is d naught, okay, minus w naught. So this is taking moments about c. Okay, taking moments about c, so we have fa into h, I'm sorry, ff into h, so this is this moment, and also add to fa into d naught by 2, and this is the negative, that's all. Okay, so this gave the three equations. So let us number them. So this is 1, 2, 3, 4, 5, and 6. Okay, so there are 9 equations, and from your understanding of the number of equations and number of unknowns, so you very well know that in this kind of linear algebraic equations, so the number of unknowns should be equal to the number of unknowns. Okay, so there are 9 equations which we have come across, and out of which how many unknowns are there? So unknowns are 1, 2, 3, 4, 5, and 6. What are the unknowns? So the unknowns are ABC, FA, FB, FC, and what else? FD, FE, F. So there are 6 unknowns, and number of equations are seem to be 9. So what is the fallacy here? So are we having more number of equations, or did I forget any unknowns? So if you look at this, it's a very interesting thing. So whenever you formulate the equations of equilibrium of different bodies here, so we should, before we proceed to solving this one, we should make sure that the number of unknowns are equal to number of equations. So what is the thing which we have done something wrong here? Have we done something wrong here? Look at this thing again carefully. So I've taken the system as a free body diagram. Container and ball 1 and ball 2. So the interesting part is that if these three are in equilibrium, is there any necessity of talking about the system being under equilibrium? So it is this way. So if a system is under equilibrium, every part of it is also under equilibrium. Or on the other hand, if the inside components, if each and every component of the system is in equilibrium, then the system is under equilibrium. So that means that we are unnecessarily writing equations or considering the free body diagrams unnecessarily. So if these three are in equilibrium, then this need not be considered, right? Okay, because if the container, ball 1 and ball 2 are under equilibrium, so the whole system is under equilibrium. So that means that if you are considering equations 3 to 9, that's good enough. Okay, 3 to 9 is good enough and 1 to 3 is not necessary. I hope you are following that. So because these three are under equilibrium, it implies that the system is under equilibrium, and writing down these equations is not necessary. In fact, if you can manipulate these equations 3 to 9, you can write this 1 to 3 also. So this 1 to 3 will not give you any further information. Okay, so like that. So that means that we can forget about this one and we will try to manipulate only that. So these two equations are no more necessary for us. And then let's once again look at carefully. So we have 7 equations, right? Yeah, we have 7 equations, and then we have 6 unknowns. So here also that means that there is one equation which is not necessary, which can be obtained from the other one. So which is there. So if you want to use it, I mean, it's implied, it is there, but it is not useful. For example, I can even tell that if you combine these two equations, for example, this one and this one, this one and this one, okay, 6 and 8 equation. So 6 and 8 equation, if you add them, what is that you get? 6 and 8 equations, and if you get it, what do you get? Equation number 3. So that means that if these two balls, it's also possible that if these two balls also can be considered to be together under equilibrium. So that's also is possible. If that is the case, then if 6 and 8, if you add together, 6 and 8 equations imply, can you see that? So they imply number 3, third equation. So that means that this is either you consider these two, or you can neglect one of it and consider only 2. Out of these 3 equations, only 2 are independent. So that's another trivial thing which is there. So let us see how to solve this one. Okay, so another interesting thing also is that we can solve all these equations together and get all these FA, FP, FC, FD, all these 6 unknowns. But on the other hand, if you are interested only in finding out FA and FC, because that's what our ultimate question, whether it is going to tip or not, so FA and FC. So let us look at that one. So for that, once you solve a number of problems, so instead of going like this one, in fact, if you are a computer wizard, you can put it through the computer and then formulate the 6 equations, 6 unknowns. You can get the inverse. I mean, if you have the numbers and all that, so you can put that one. So another, of course, here I forgot to tell you what phi is. This is phi. This phi, you can see that this horizontal distance is nothing but, if the vertical distance is h, and horizontal distance is S. So S, you can see that d naught minus small d, because this is d by 2, this is d by 2, subtract it, so it's d by 2. And then this ABCD PQ, the distance between P and Q is nothing but diameter d, and so we have cos phi as d naught minus d. So depending upon the geometric parameters, so we can also get cos phi, and in that process you can also get h. So h is nothing but d sin phi, and s is d cos phi. So wherever you have any of these h and all that, you can make use of these geometric values. All right, so to simplify this, so let us look at these things again. Is that let's consider, so to simplify these equations, another thing which we can do is that we can even consider balls 2 and 3, 1 and 2 together. As a free body diagram. So this is the beauty of it, of free body diagrams. This is the beauty of this static equilibrium. So where you can consider the whole system under equilibrium, or even a part of it, any part of that is also under equilibrium, depending upon your convenience. So if you want to eliminate this Fe, for example, avoid that and make a simpler thing. So we can put the bodies together, 1 and 2. This P and Q together like this. And this is W1 and W2. And of course, don't forget to show this FB also. And you have FT. So of course, FT and FF. Of course, it's very easy to see the horizontal equilibrium equations imply that FD is equal to FF, right? So this is horizontal. And vertical, also you can put it as FB is equal to W1 plus W2. And so if the FD and FF are same, so either you can use FF or something like that. So then we can find out the moment. So the moment equation about P. If you get the moment equation about P, then so FF will create a moment about this one. So that is FF times H. And then where we are taking about P, so we can eliminate this FB as well as FD. So taking the moment about P. So that means that we have FF times H is equal to W2 times the horizontal distance S. Okay. So this is, so we have solved for FF. So I'm just leaving this for the moment here. So FF is all equal to W2 times S divided by H. So S we know here, S is d cos phi, S is right, or S you can say d naught minus d. So either of it is fine. And H is d sin phi. Okay, so this is about FF. right? And so which is also equal to FD. Okay, so we have FD, we have FF. If you want, we can also find FB. FB is nothing but W1 plus W2. So this is also there. So we have solved it to some extent. What is that which we are looking at? So we are looking at FA and FC. So let's look at FA. So if you look at this, very interesting thing is that if these forces are there, so this is trying to rotate this one in the clockwise rotation, whereas W0 is trying to put it in the counterclockwise direction. So if there is W0, we don't have any control. It is given. Only these two forces are the ones which we have, say, control based on the geometry. So because of this, what is that? The tendency for it to tip. So because of this one, so this point A here has a tendency to lift off, right? So that means that this FA, which is probably originally it is pushing it down, so there is a chance that this point A may lose contact. And under what circumstances will it lose contact? So the FA, the force at A, if it's supposed to be positive, okay, but on the other hand, if it is going to be negative, then there is a possibility that it loses contact. So let us look at FA. So if you look at FA times, if you want to just calculate FA, right, take the moment about C, right? So this is FA times D0 minus W0 over D2, and then we have plus we have FF times H. Okay, so that means that if you want FA, then a D0 you can calculate, so it's W0, so minus FF H by D. So what is H? H is nothing but D sin alpha. FF is the whole thing. FF is this one, W2 times S divided by H times H by D0. So S is nothing but D minus. Okay, so this is the interesting part here. The forces at FA, the force at FA may be possible that it may become negative, right? So if this quantity may become negative, that means that when D becomes smaller and smaller, and also if W2, in fact, if the weights of the balls are more than the container, so there is a chance that this will become negative. So the tipping may take place. May tip about C when W2 times D minus. So there are several possibilities here is greater than. Okay. So either W2 may be heavy, or even the balls may become smaller. Okay. So small d may become smaller, and in which case it may become more than W0 by tip. So, and in this process you can also see when, because as such if there is no balls, then this is equal, these forces will be equal. Because of the balls, what happens is that this is becoming less and this is becoming more. So there is no question of tipping about A. This will never become negative. Only this FA is becoming negative, right? So I hope and of course the rest of it is that I found out what is FA. You can find out FC. It's very easy. So it is nothing but W0 plus W1 plus W2 minus FA will become FC, right? And you can also, well, there is also FB here. Well, then you can calculate FB also by coming to this equilibrium. So that much part I leave it to you. So it's a very interesting problem, looks very innocuous, but then the moment you start exploring or trying to understand this one, so a simple set of equations for the whole system is not enough. You have to go to the free body diagrams and then you have to appropriately choose the free body diagrams so that you can reach the solution much easier. There's so many other things. So every system can be done like this. I think as a last thing, probably I will just indicate is that I will not solve. So sometimes it is, so if you look at the truss problems, you will see a lot of these structures in practice. 60 degrees equilateral triangles. So if you have something like this, and there can be any number of loads. So many times in civil engineering, so we would like to find out all these things are pin joints, and so each member is subjected to only inline loading. So it's subjected to two forces at the two hinges. So that for equilibrium, that force is necessarily to be in line with those hinges. So so this one very simple. So very simple to. So there are reactions here, vertical only, right? And let me just say, so this is a truss problem, and then many times you would like to find out what is the, say, A, B, C. So many times you would like to find the force in AB. So if this is, what is that if you want to find out the force in AB? So only thing is that you have to cut it there, okay? And consider these two as two separate free body diagrams. Consider one of it. Consider one of it as free body diagram. Cut the structure at AB. Okay, so what essentially is that? So I cut it here. So essentially the force in the three members, so these are the truss members. So we know that the force here, this is what do you call it as D here. So this is FBD, no, FAB, and this is FDB, and this is E, this is F. So there are three forces acting on these three members, and axially, obviously, because this, we know that the force in these members is along the direction of the axis. So there's an FAB, there's FDB and FDE. So there are three forces. We know the directions, they are all at 60 degrees or horizontal. And if you want to find out FAB, what is the best thing again? So this, if you extend this one to point D here, then take the moments about D about, okay, and solve for FAB. So FDB and FDE will not have any moments about D. So it will be FAB times H times is equal to W2 times L and 2L. Okay, so it's very simple here. So FAB into H is nothing but W2 times twice L. This is H. What is H? It's an equilateral triangle, so H is nothing but L times root 3 by 2. Okay, so this is, I just indicated. So that means that when you draw the free body diagram, you can judiciously cut it in this kind of truss structures so that you will end up with only three unknowns, and you can apply three equilibrium equations. So at this moment, we'll stop this the two-dimensional analysis of these structures and mechanisms, and we'll move on to the three-dimensional structures. Okay, so for the moment, it's bye-bye.